welcome to this problem walkthrough. Today, we'll tackle LeetCode number 1395, count number of teams. This problem challenges us to analyze an array of ratings and count the number of valid teams of size 3 that meet specific criteria. Let's dive in and explore the problem step by step. In this problem, you're given an array of integers called rating. Each element in this array represents the rating of a soldier positioned in a line. Your goal is to identify and count the total number of possible teams of exactly 3 soldiers. A team is considered valid if the ratings of the 3 soldiers meet one of the following conditions. First, the ratings must be strictly increasing, meaning the first soldier's rating is less than the second soldier's, and the second soldier's rating is less than the third. Alternatively, the ratings can be strictly decreasing, where the first soldier's rating is greater than the second, and the second is greater than the third. In both cases, the indices of the soldiers in the team must follow the order I less than J less than K. This means the soldiers must appear in the same sequence in the line as they are chosen for the team. Your task is to calculate the total number of teams that satisfy either of these conditions, and return that number as an integer. Consider the first example where the input rating is 2, 5, 3, 4, 1. The output in this case is 3, indicating there are 3 valid teams. Let's break this down. The first team is 2, 3, 4, which satisfies the strictly increasing condition because 2 is less than 3, and 3 is less than 4. The second valid team is 5, 4, 1, where the ratings are strictly decreasing as 5 is greater than 4, and 4 is greater than 1. Finally, the third team is 2, 5, 1, where the ratings follow a mixed pattern. Here, 2 is less than 5, and 5 is greater than 1, still meeting one of the specified conditions. Since there are no other triplets in this array that meet the criteria, the total number of valid teams is 3. Now, let's look at another example where the input rating is 2, 1, 3. In this case, the output is 0. This is because there are no triplets in the array that satisfy either the strictly increasing or strictly decreasing conditions. For instance, while the elements 2 and 3 do increase, there is no valid middle element that allows the triplet to satisfy the increasing order with I less than J less than K. Similarly, no combination of 3 indices meets the condition for strictly decreasing ratings. Therefore, the result is 0, as no valid teams can be formed. Finally, let's examine the last example where the input rating is 1, 2, 3, 4. This time, the output is 4, as there are 4 valid teams. These teams are 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. All of these triplets satisfy the strictly increasing condition because for each triplet, the ratings are ordered such that the first soldier's rating is less than the second, and the second is less than the third. This example also illustrates how larger arrays with a clear increasing or decreasing pattern can lead to multiple valid teams. To summarize, the problem's constraints ensure that there are always at least 3 soldiers, and the edge cases include situations with identical ratings or arrays that are fully increasing or decreasing. By carefully evaluating all possible triplets, we can determine the total number of valid teams. The problem count number of teams challenges us to identify all valid teams of 3 soldiers based on their ratings. Specifically, we need to find triplets where the ratings are either in strictly increasing order, like rating I, rating J, rating K, or in strictly decreasing order, like rating I, rating J, rating K. The key difficulty lies in efficiently counting these combinations, especially when the input size is large. One straightforward way to approach this is the brute force method. Here, the idea is simple. We iterate through all possible triplets of indices I, J, K, with I less than J less than K, and for each triplet, we check if the ratings satisfy either the increasing or decreasing condition. For every valid triplet, we increment our count. While this idea is easy to understand and implement, it involves 3 nested loops, one for each index, making it computationally expensive for large arrays. This inefficiency is an important limitation we'll aim to address with better strategies. The brute force approach, though intuitive, has significant drawbacks due to its computational cost. Each triplet requires 3 nested loops, leading to a time complexity of n cubed. While this may work for small input sizes, it becomes impractical as the array size grows, especially when n approaches 10,000. On the positive side, this approach is very straightforward and requires no additional memory, so its space complexity is O(1). However, the extreme slowness for large inputs makes it unsuitable for this problem. To improve, we can adopt the optimized approach, which leverages the idea of counting smaller and larger elements relative to the middle soldier in a potential triplet. Instead of exhaustively iterating over all triplets, we focus on each soldier as the middle element, rating j, and count the smaller elements to its left and larger elements to its right. Similarly, we count the larger elements to its left and smaller elements to its right for the decreasing condition. Using these counts, we can directly compute the number of valid teams involving rating j, without iterating over all triplets. This drastically reduces the number of operations needed. The optimized approach improves efficiency by reducing the time complexity to O(n²). For each middle soldier rating j, we count smaller and larger elements on both sides using nested loops, which is far more efficient than the brute force approach. The space complexity remains O(1), as no additional memory is required. This balance of simplicity and performance makes it a significant improvement. However, implementing the counting logic carefully is crucial to ensure correctness. For even greater efficiency, we can use advanced data structures like Fenwick trees, also known as binary index trees, to count smaller and larger elements in logarithmic time. By maintaining the frequency of elements dynamically, we can calculate the required counts in O log n per query. This reduces the overall time complexity to O(n log n). The steps include using the Fenwick tree to track the frequency of elements as we iterate through the array. For each element, we query the tree to determine the counts of smaller and larger elements on either side and compute the number of valid teams as before. While this approach is faster, it introduces the additional complexity of implementing and managing a Fenwick tree. The Fenwick tree approach is the most efficient in terms of time complexity, making it ideal for very large inputs. However, it comes with the trade-off of requiring a solid understanding of advanced data structures, which might make it harder to implement for some users. After evaluating all options, the optimized approach strikes the best balance between simplicity and efficiency. The brute force method, while easy to code, is far too slow for larger inputs. On the other hand, the Fenwick tree approach, despite its speed, is more complex to implement and may not be necessary for moderately sized inputs. The optimized approach achieves significant performance gains compared to brute force by capitalizing on the observation that the middle element uniquely determines the triplet. By counting smaller and larger elements on either side of the middle soldier, we avoid iterating over all possible triplets. This reduces the complexity from O(n³ to O(n²), making the solution scalable and practical for larger arrays. With a clear implementation of the counting logic, this approach provides an excellent trade-off, making it the preferred choice for solving this problem efficiently. To solve the problem of counting the number of valid teams, we need to form groups of 3 elements from the input array rating. These groups must either be in strictly increasing order, where the first element is less than the second, and the second is less than the third, or in strictly decreasing order, where the first element is greater than the second, and the second is greater than the third. To achieve this, we will use an optimized approach with a time complexity of O(n²). First, we initialize a variable count to 0, which will keep track of the total number of valid teams. The input array rating has a size of n, and each element represents a rating value. The key idea is to treat one element at a time as the middle member of a potential team. We iterate through the array, designating each element rating, j, as the middle element, and systematically evaluate whether valid teams can be formed around it. When an element rating, j, is treated as the middle member of a team, we need to count the number of elements smaller and larger than rating, j, on both sides of it. Specifically, for each j, we calculate 4 values, left_smaller, which counts how many elements to the left of j are smaller than rating, j, left_larger, which counts how many are larger, right_smaller, for elements to the right that are smaller, and right_larger, for elements to the right that are larger. These counts allow us to determine the number of valid teams. For teams in increasing order, we add left_smaller * right_larger to the total count, as these represent combinations where rating I, rating j, rating k. Similarly, for teams in decreasing order, we add left_larger * right_smaller to the total count, representing combinations where rating I, rating j, rating k. After iterating through all possible middle elements, we return the final value of count as the result. The decision to treat rating, j, as the middle element simplifies the problem significantly. By fixing the middle element, we reduce the task to counting smaller and larger elements on either side, which can be done efficiently. Unlike some approaches that pre-compute these counts for every element, our method calculates them dynamically during the iteration, ensuring low space usage with a space complexity of O(1). This optimization avoids the inefficiency of a brute force O(n)³ solution, which would involve checking all possible triplets individually. Additionally, the algorithm only relies on scalar variables like count, left_smaller, and right_larger, without needing any additional data structures, making it both memory efficient and straightforward to implement. The input array rating remains unmodified throughout the process, as we simply traverse it to extract the necessary counts. Analyzing the complexity of the algorithm, we find that the time complexity is O(n²). This comes from iterating through the array for each middle element and counting smaller and larger elements on both sides, which takes linear time for each middle element. The space complexity is O(1), because we only use a constant amount of additional space, regardless of the input size. It's important to consider edge cases to ensure the algorithm handles all situations correctly. For example, if the input array has fewer than 3 elements, no teams can be formed, so the output should be 0. Similarly, if all elements in the array are equal, it is impossible to form valid teams because the conditions require strict inequality. For sorted or reverse-sorted arrays, the algorithm correctly identifies all possible teams without any special handling, as the counts are computed dynamically for each middle element. To illustrate the algorithm, let's walk through an example with the input array rating equals 2, 5, 3, 4, 1. When j equals 1, the middle element is rating, j equals 5. To the left of j, there is one smaller element, 2, so left_smaller equals 1, and no larger elements, so left_larger equals 0. To the right of j, there are 3 smaller elements, 3, 4, 1, so right_smaller equals 3, and no larger elements, so right_larger equals 0. Using these counts, the number of valid teams with j equals 1 is calculated as left_smaller asterisk right_larger plus left_larger asterisk right_smaller equals 1 asterisk 0 plus 0 asterisk 3 equals 0. Repeating this process for all other indices j, we accumulate the total count of valid teams. For this input, the final output is count equals 3, representing the total number of teams that can be formed in either increasing or decreasing order. This implementation solves the problem of counting the number of valid teams of size 3. A valid team can be formed either in strictly increasing order, rating I, rating j, rating k, or in strictly decreasing order, rating I, rating j, rating k, or I less than j less than k. The key insight here is to treat each element in the array as the middle element of the team, rating j. For each such middle element, we count how many numbers to its left and right satisfy the conditions for forming a valid team. 1. Outer loop. We iterate through the array with j ranging from 1 to n2, since j must always have at least one element on both sides. 2. For each j, we compute left_less and left_greater. These represent the count of elements to the left of j that are smaller or greater than rating, j, respectively. Right_less and right_greater. These represent the count of elements to the right of j that are smaller or greater than rating, j, respectively. 3. Using these counts, we calculate the number of valid teams where j acts as the middle element. Teams in increasing order, left_less asterisk right_greater. Teams in decreasing order, left_greater asterisk right_less. 4. The total count is updated by summing the contributions from both increasing and decreasing teams. This approach ensures that we check all possible valid combinations efficiently. The overall time complexity is O(n²), because for each middle element j, we perform 2 linear scans, one for the left and one for the right. The solution is both optimal and clean, making it well suited for this problem. Here, we start with the Java implementation of the problem. The method numberTeams takes an array of integers called rating, which represents the ratings of soldiers. The goal is to count the number of valid teams we can form. First, we initialize n as the length of the array and count to keep track of the valid teams. Then, we use a for loop where the variable j represents the middle soldier in the team. This loop starts at index 1 and goes up to n2, since the middle soldier cannot be the first or last element. Next, we use two variables, left less and left greater, to count how many soldiers to the left of j have a rating less than or greater than the rating of the middle soldier. Similarly, we define right less and right greater to track the count of soldiers to the right of j with ratings less than or greater than rating j. Within the inner loop, we iterate through all indices before j to compute the left counts. If a soldier's rating is less than rating j, we increment left less, otherwise, if it's greater, we increment left greater. Then, in another loop, we count the soldiers to the right of j using the same logic, updating right less and right greater accordingly. Once we have the counts for soldiers on both sides of j, we calculate the number of valid teams with j as the middle soldier. A valid team can be formed either by combining left less soldiers with right greater soldiers or by combining left greater soldiers with right less soldiers. This is because a team is valid if the ratings strictly increase or strictly decrease. We add the total number of such teams to the count variable. Finally, after iterating through all possible middle soldiers, we return the total count of valid teams. This implementation works efficiently by focusing on the middle element and counting the valid combinations on either side, ensuring we meet the problem's constraints. To solve this problem, we start by analyzing the input array rating equals 2, 5, 3, 4, 1. First, we initialize two variables, n, which is the length of the array, and count, which will keep track of the total number of teams. Here, n is 5 and count starts at 0. Now, the approach involves selecting each index j as the middle element of potential teams, and for each j, we calculate how many elements to the left are smaller or greater than rating j, and similarly, how many elements to the right are smaller or greater. Let's consider j equals 1, where the middle element is rating 1 equals 5. We initialize counters left underscore less, left underscore greater, right underscore less, and right underscore greater to 0. Looking at the left side of j, we only have one element, rating 0 equals 2, which is less than 5. So, we increment left underscore less to 1. On the right side, we examine the elements rating 2 equals 3, rating 3 equals 4, and rating 4 equals 1. All three are less than 5, so right underscore less becomes 3. Using these counts, we calculate the number of valid teams formed with j equals 1 as the middle element. The formula is count plus equals left underscore less asterisk right underscore greater plus left underscore greater asterisk right underscore less, which in this case evaluates to 1 asterisk 0 plus 0 asterisk 3 equals 0. Thus, no valid teams are formed for this value of j. Next, we process j equals 2, where the middle element is rating 2 equals 3. Again, we reset the counters left underscore less, left underscore greater, right underscore less, and right underscore greater to 0. Looking to the left of j, we find two elements, rating 0 equals 2 is less than 3, so left underscore less becomes 1, and rating 1 equals 5 is greater than 3, so left underscore greater becomes 1. On the right side, we have rating 3 equals 4, which is greater than 3, so right underscore greater becomes 1, and rating 4 equals 1, which is less than 3, so right underscore less becomes 1. Using the same formula for counting teams, we calculate count plus equals left underscore less asterisk right underscore greater plus left underscore greater asterisk right underscore less, which evaluates to 1 asterisk 1 plus 1 asterisk 1 equals 2. This adds two valid teams to our total. Now, we consider j equals 3, where the middle element is rating 3 equals 4. As before, we reset all counters. Looking to the left, we examine rating 0 equals 2, which is less than 4, so left underscore less becomes 1, rating 1 equals 5, which is greater than 4, so left underscore greater becomes 1, and rating 2 equals 3, which is less than 4, so left underscore less increases to 2. On the right side, there is only one element, rating 4 equals 1, which is less than 4, so right underscore less becomes 1. Using the formula, we find count plus equals left underscore less asterisk right underscore greater plus left underscore greater asterisk right underscore less, which evaluates to 2 asterisk 0 plus 1 asterisk 1 equals 1. This adds one more team to our total. Now that we've processed all possible middle elements for the first example, the total count of teams is 0 plus 2 plus 1 equals 3. Let's move on to the second example, where the input is rating equals 1, 2, 3, 4. We start again by initializing n equals 4 and count equals 0. For j equals 1, where the middle element is rating 1 equals 2, we reset the counters. To the left, there's only one element, rating 0 equals 1, which is less than 2, so left underscore less becomes 1. Looking to the right, we have rating 2 equals 3, which is greater than 2, so right underscore greater becomes 1, and rating 3 equals 4, which is also greater than 2, so right underscore greater increases to 2. Using the formula for counting teams, we compute count plus equals left underscore less asterisk right underscore greater plus left underscore greater asterisk right underscore less, which evaluates to 1 asterisk 2 plus 0 asterisk 0 equals 2. This adds 2 teams to our total for j equals 1. Finally, we process j equals 2, where the middle element is rating 2 equals 3. After resetting the counters, we look to the left and find rating 0 equals 1 and rating 1 equals 2, both of which are less than 3. This makes left underscore less equals 2. On the right, there's only one element, rating 3 equals 4, which is greater than 3, so right underscore greater becomes 1. Using the formula, we calculate count plus equals left underscore less asterisk right underscore greater plus left underscore greater asterisk right underscore less, which evaluates to 2 asterisk 1 plus 0 asterisk 0 equals 2. Adding this to the total, we find that the total count of teams for this input is 2 plus 2 equals 4. In summary, this approach systematically selects each element as the middle of a team, counts smaller and larger elements on both sides, and combines these counts to compute the total number of valid teams. The time complexity of this solution is n squared, since we use nested loops to examine the elements to the left and right for each potential middle element. To analyze the time complexity of the algorithm, let's start by considering the outer loop, where the variable j iterates through the array, representing the middle element of the triplet. This loop runs n 2 times, which simplifies to n, since n is the size of the rating array. Next, for each value of j, the first inner loop iterates over all indices before j, specifically j times. In the worst case, when j is near the middle of the array, this loop performs about n/2 iterations. Summing up these iterations across all values of j gives us an arithmetic series whose total is proportional to n squared. Similarly, the second inner loop iterates over all indices after j, running n and j 1 times for each middle element. When summed across all j, this also results in an arithmetic series summing to n squared. Thus, both inner loops contribute n squared operations in total. Inside these nested loops, the operations performed are simple comparisons and arithmetic computations, like incrementing counters, which each take constant time, or O1. Since these operations are dominated by the number of iterations in the inner loops, their contribution to the time complexity does not change the overall analysis. Combining the outer loops n with the n squared contributions from the inner loops, the total time complexity of the algorithm is n squared, which simplifies to n squared. As for space complexity, the algorithm uses a fixed number of variables, such as count and the loop variables, which together require O1 space. Since the input array is read-only and no additional data structures are used, the total space complexity of the algorithm remains O1. This makes the solution efficient in terms of both time and space. To put this into perspective, let's compare the current approach to a brute force solution. A naive method would involve 3 nested loops to generate all possible triplets and check whether each one satisfies the conditions. This would result in a time complexity of n cubed, as the 3 loops iterate over the array independently. However, with the current approach, we avoid explicitly generating all combinations by strategically counting valid triplets, which reduces the time complexity to n squared. Importantly, the space complexity remains the same, O1, for both approaches since no additional storage is required beyond a fixed number of variables. Furthermore, analyzing the best, average, and worst cases, we find that the time complexity is consistently n squared, regardless of the input. This is because the algorithm always performs the same number of iterations, as it is solely dependent on the size of the input array and rather than its content. Finally, to mathematically justify the time complexity of n squared, consider the dominant factor, the nested loops. Each inner loop's iterations contribute to an arithmetic series that sums to O n squared, and this is combined with the O n outer loop. Constant time operations inside the loops do not affect the overall complexity, as they are negligible compared to the O n squared iterations. For space complexity, the algorithm's use of fixed variables results in a constant space requirement, or O1. Since no additional space is allocated for data structures beyond what is necessary for the input in variables, the space complexity remains optimal. This balance of O n squared time and O1 space ensures the algorithm is both efficient and scalable for larger input sizes. When solving this problem, there are several common mistakes to watch out for. First, it's essential to correctly handle both increasing and decreasing sequences. This means you should identify teams where the ratings satisfy either rating I, rating J, rating K, or rating I, rating J, rating K. Missing one of these conditions results in an incomplete solution and incorrect results. Next, many beginners use three nested loops to brute force all possible team combinations. While this approach does work for small inputs, it's inefficient for larger arrays, leading to a time complexity of O n cubed, which can make the solution impractical when n is large, such as 1000. Another frequent issue is incorrect index handling. Remember, the indices must follow the condition I less than j less than k. Failing to enforce this ordering can lead to invalid teams or duplicate combinations being counted. Lastly, edge cases are often overlooked. For example, you may encounter arrays with fewer than 3 elements, arrays containing duplicates, or those with values near the constraint limits. Not accounting for these scenarios can cause runtime errors or produce inaccurate results, so it's important to validate your solution against such cases. Another mistake is overcomplicating the solution. Some approaches attempt to precompute all combinations or use unnecessarily complex data structures, which can increase both the code complexity and the likelihood of bugs. Instead, focus on simplicity and efficiency. Now, when this problem appears in interviews, it's important to highlight a few key insights. First, think carefully about the relationship between indices and values. Since I less than j less than k must hold, avoid recalculating relationships that can be precomputed. For example, using prefix sums or precomputed counts for smaller and larger values can reduce the time complexity to O n squared. This optimization not only improves runtime but also demonstrates your ability to recognize and address inefficiencies. During an interview, it's also critical to discuss the trade-offs between different approaches, such as brute force versus optimized solutions. This shows that you can evaluate and justify the choices you make. Finally, always demonstrate awareness of edge cases. Handling scenarios like small input sizes or duplicate values shows thoroughness and attention to detail, which interviewers highly value. To deepen your understanding of this problem, it's helpful to explore related problems on LeetCode. For example, problem 300, longest increasing subsequence, focuses on identifying increasing subsequences, which is a similar concept. Problem 673, number of longest increasing subsequences, builds on this by adding constraints to the subsequences. Problem 121, best time to buy and sell stock, involves finding optimal subarray relationships, which, while not directly related, shares some underlying principles. Additionally, problem 376, wiggle subsequence, explores sequences with alternating increases and decreases, which may help you think about sequences in new ways. Now, when it comes to solving this problem, there are different approaches you can take. The brute force method uses 3 nested loops to iterate through all possible teams and checks the conditions. While this is simple to implement, its O n cubed complexity makes it inefficient for large inputs. A more optimized approach is the 2-pass solution. Here, for each index j, you count valid I indices, or I less than j, and valid k indices, or k greater than j, using prefix sums or precomputed counts. This reduces the time complexity to O n squared, making it a much better choice for larger input sizes, though it does require a bit more effort to implement. For even greater efficiency, advanced data structures such as Fenwick trees or segment trees can be used. These structures allow you to count smaller and larger elements efficiently, reducing the time complexity to O n log n. This approach is particularly useful for scenarios with stricter performance constraints. However, it does require a deeper understanding of these data structures, and the implementation can be more challenging, especially in an interview setting. While this method is powerful, it's important to weigh its complexity against the problem's requirements and the context of the discussion. Mastering such techniques can set you apart, but always ensure that your solution is both correct and appropriately optimized for the situation at hand. Great job! We've just completed the walkthrough for LeetCode number 1395. In this problem, we explored how to count valid teams based on specific criteria. It's a great exercise for practicing array manipulation and conditional logic. Thanks for watching, and make sure to like and subscribe for more coding tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!